I want to spend some time with you going over a concept that I know you learned about in freshman chemistry. It's called Gibbs free energy. A lot of times you'll see it as GFE. And simply stated, it's the amount of change of energy during a reaction, either energy being consumed by the reaction or energy being generated from the reaction itself. So the Gibbs free energy equations are varied. It depends upon what system you're trying to apply it to. So you may, in freshman chemistry, have seen Gibbs free energy in this form, where you have delta, meaning change of Gibbs free energy, is equal to delta H, where H is enthalpy, minus the temperature of the system in Kelvin times delta S, which is entropy. So that's again applying in a more physical chemistry type of context. What I'm wanting to do now, let me get the enthalpy there. What I'm wanting to do now is to apply Gibbs free energy into the context of moving things in and out of a cell. So what I say here is the movement of any molecule, non-charged, down or up a concentration gradient involves a change, there's my delta, in free energy, Gibbs free energy. And of course, call that delta G. So stated kind of simply, if I'm having a particle going down its concentration gradient, then it's going to release energy by definition, and that means that delta G is going to be negative. So negative delta G always means a release of energy. And so again, a particle going down its concentration gradient is releasing energy. If a particle is moving up the concentration gradient, pushing against the concentration gradient, that is going to require a consumption of energy. In other words, I'm going to have to put energy into the system to move a particle against its concentration gradient. So if I'm doing that, then that means delta G must be positive. So positive, the way you remember this, positive meaning adding energy into the system. And if you're having to add energy into a system to move a particle across the cell membrane, then by definition you're moving that particle against a concentration gradient. So there is a formula that helps us with these types of calculations, and this is it right here. And this is simply stated: delta G, N is an IN, is equal to R. R is going to be gas constant. It's going to be 2, times the temperature of the system in Kelvin, times the natural log of the concentration of the particles inside the cell over the concentration of the particles outside the cell. So this is the formula you always use. And so there's an assumption here that's very important for us to understand. So we can imagine we have a cell, and of course we're going to let that be our extracellular fluid, our intracellular fluid here. And then if I have a particle on the outside of the cell and it is moving into the cell, assuming that the cell membrane is permeable to it, then this is when this equation here applies. So let's do another example here. What did I just tell you? I just told you if the particle is moving down the concentration gradient, that the delta G is going to be negative. Well, in this scenario here, I've got more X on the outside, a little bit of X on the inside. It is so because I'm drawing it that way. So the big X means more X, all right? And the small x means less X. So I'm looking at that. If I let this system go, X is going to go down its concentration gradient. And what I'm telling you is, then by definition, then delta G is negative. All right. So coming over here, again, now let's just say I've got a little bit of X here, okay, and then a lot of X here, okay, you get ECF, ICF. And again, suppose that, say, okay, I want to move this X from outside to inside, just like what I do here. Well, ask yourself the question, looking at these concentrations of X's, I want to move the X's from outside to inside, which is what this equation here is assuming. I'm assuming that I want to move the X's from outside to inside. I know by looking at this then that my delta G is going to be positive. How do I know it's going to be positive? But because if I'm going to move the small quantity of X on the outside to the inside, I'm going to have to add energy into the system. So that makes that positive. So this is one of the foundational concepts that I want to get your mind around when you're looking at the equation in this form. And it's important that you know that the concentration on the inside must be on the top of this quotient, and then outside must be on the bottom. And then when you do that, the delta G, or the Gibbs free energy you are calculating, is assuming trying to move the particles from outside to the inside. Now, whether when you run this calculation and you actually put in values here, whether it is positive or negative, is going to let you know what your concentration gradient is. If it's negative, I know I got more X on the outside than I do the inside. So in a sense, from an energy perspective, the ball is rolling down the hill. Okay? But if I run this calculation and I get delta G to be positive, then what that tells me is, okay, if I'm going to take this X from the outside inside, I'm going to have to add energy into the system. Therefore, the delta G must be positive. Okay, so let me develop this a little bit more, and this is kind of basically the same thing what I just told you. The delta G in means the energy either released or must be put into the system for the molecule to move from the ECF into the ICF. And again, this formula up here is assuming out to in when it comes moving a particle across the cell membrane. Okay, the assumption is I want to move the particles into the cell. Now the concentration gradients, it depends on the situation, but that's what this formula here is assuming. So stated kind of in another way, what this really means is when X in the cell is less than X out the cell, delta G is going to be negative. Okay, you can draw the picture, same picture I drew earlier. Okay, so X in the cell is less than X out of the cell, so a little bit X here, big X there, delta G is negative. Or when X in is more than X out, then the delta G will be positive. So I got X in is more, bigger, out smaller, then I know my delta G is going to be positive, which means if I want to move that X in there, I'm going to have to put energy into that system. Okay, so those are kind of some foundational concepts that I want you to think through, make sure you have a basic understanding here. So let's do some examples, and what I'm going to do is I'm just going to kind of apply this formula here a little bit, and so let's take a look and see what we can do with that. Okay, again, I'm going to go with my same example here. I got a cell here, lots of X here, a little bit of X there. So again, the equation that we have up here assumes out to in. So I'm looking at this, and I'm being asked to calculate a Gibbs free energy. I'm not going to give actual concentrations. I'll do that in another lecture. But looking at this system here, what do you already know? You already know that delta G will be negative. Why? Because it's going down its concentration gradient and it's going to be releasing energy. The ball is rolling down the hill, so energy is released. So in a sense, you could say, all right, well then that means I have a force. I'm just going to put a vector here. And as you know, vector magnitude and direction. So its magnitude is a concentration gradient, and the vector tells you that the net force is moving the x into the cell. Now suppose you did some calculation and you said, okay, I do this. If I had some numbers here I could put in terms of concentration, and then you calculated it out and you found out that delta G equals -2 kilocalories per mole. Okay, you applied this equation up here, you punched in some numbers there, and that's what it turned out to be. Well, then that means that this vector here is symbolizing 2 kilocalories per mole of energy being released. So now here's my next question, and this is kind of fun and interesting to think about. What if I wanted to put energy in the system, put energy on those X's, and I wanted to stop those X's from going into the cell? I want to push back. So I want to have a vector in that direction, and I want to push against that concentration gradient. I'm putting energy into the system, okay? So the question is, how much energy would I have to put into the system to stop those X's from going into the cell? I'm pushing back against the X's. I want to bring it to some type of equilibrium as I'm putting energy in the system. Well, you know, then these vectors here have to be in opposite but also equal magnitude to bring this system into equilibrium. So then the question is, if I'm adding into the system, and that's what this vector here is symbolizing, what are the kilocalories that I must add into the system to bring this thing to equilibrium? And okay, so I think the answer is pretty straightforward. Delta G is going to be equal to plus 2 kilocalories per mole to stop X from flowing into the cell. Now I'm assuming again that the cell membrane is permeable to X. So that's what that would be. So then the next question is, okay, how much energy in the system in terms of pressing on the X's would it take for me to start moving the X's from inside the cell to outside the cell? Well, again, I think the answer is fairly straightforward. Delta G must be greater than plus 2 kilocalories per mole. Okay? So if I were to ask you a question, show you this system here and give you the values of the X's outside to inside, and then ask you, okay, how much energy would it take to make this X here leave the cell? The first thing you're going to do is to calculate the Gibbs free energy of the system, and what you're going to get is that number there from this equation here, and that's telling you X goes down its concentration gradient, it's going to be releasing that energy there. And then you flip the sign from minus to plus 2, which means that's the amount of energy that you're going to stop any X's from coming into the cell. And then you know, okay, well, if I'm going to make the X's leave the cell going up its concentration gradient, then the energy input must be greater than 2 kilocalories per mole. So that's how that works. That's the thought process. So let's do another example. So how about we're just going to reverse it? We got that there. And now I have a little bit of X here. And I have a lot of X here. And now I'm asking you, okay, how much energy am I going to have to put into this system such that I'm driving X into the cell? First of all, I can look at that. Again, the convention is out to in. That's what this equation here is assuming. So you plug those numbers in, and let's just suppose that you calculate and you get a G value of, say, plus 3 kilocalories. You knew it had to be positive, because if I'm going to move this X into the cell, I'm going to have to push it against this concentration gradient. Therefore, right off the bat, you know that G has to be positive. So you run that calculation, and then you get G being plus 3 kilocalories per mole. So let's pause there. Let's not fall in a trap here. So here's a potential trap. Let me elaborate for you. So if the X is going to be, the energy is going to be plus 3 kilocalories, so that means I have a vector force, okay, and I'm putting a vector force in that direction there, and that's going to be my 3 kilocalories here, okay, right there. Well, I know that the X wants to leave the cell, and so what's the force that X is doing to leave the cell? Well, it's just flipping the sign here. So I know that the force where X is going to leave the cell is going to be minus 3 kilocalories. You see that? And so if I put 3 kilocalories in the system, in terms of acting on X energy-wise, all I'm doing is I'm counterbalancing the energy of the X that's going to be released if it left the cell, right? So that would put it in equilibrium. So then the question is, how much energy would I have to put into this system such that I'm driving X into the cell? And again, the answer is delta G must be greater than positive 3 kilocalories. The 3 kilocalories is just going to bring me to equilibrium. I need to make that vector to be bigger. Okay, I've got to up that vector there, so it's going to be greater than 3 kilocalories per mole. And so that would be the answer to that. Okay, so we're going to do in the next lecture some actual calculations, but I need for you to kind of get your mind around understanding these basic concepts, you know, when I'm going to have equilibrium and when I'm going to have a net force moving the X either in or out of the cell. But again, one last time, because it's really important you understand this equation in this form, I am assuming that we're wanting the particles to go into the cell. And again, the concentration gradient may favor it or it may not favor it, but whether it favors it or doesn't favor it, you'll find out when you discover if the G is negative or if the G is positive. Okay, so we'll pick back up and actually plug in some real numbers, and hopefully as we work these, the concept will become gradually clear to you. What I want to do now is take the concepts that we talked about in the last lecture and apply it to a specific example, and we're going to focus on glucose. So let's just imagine that I have a cell here, and I've got some glucose inside the cell, and it's going to be 0.1 millimolars or millimoles per liter. And let's just suppose on the outside of the cell I have 5 millimoles per liter. Obviously, I have a concentration gradient. And so what I'm interested in here is if glucose is diffusing down its concentration gradient, how much energy is going to be released. And based on what we talked about last time, I can look at this setup here and know that whatever the calculation I come up with in terms of Gibbs free energy, it's going to be negative because, in a sense, the ball is rolling down the hill. I'm going with my concentration gradient high to low, so I'm going to be releasing energy, therefore the Gibbs free energy is going to be negative. So the other thing that I want to say here is we learned earlier that glucose doesn't cross the cell membrane. Okay, the cell membrane is fairly impermeable to glucose, but glucose can diffuse down its concentration gradient across the cell membrane if it has the correct type of transporters there. And so this is what we mean by facilitated diffusion, that there's got to be a transporter here that will grab that glucose, allow it to go down its concentration gradient. Again, it's going downhill, so it doesn't need energy, but it does need that transporter to make this work. And so when we say permeable here, I'm just assuming that the transporters are making it permeable. So I just don't want to be confusing on that point there. So we're just, again, assuming permeable means I've got the appropriate transporters there to allow glucose to diffuse down its concentration gradient. So we got our handy-dandy formula here. And again, this is Gibbs free energy in, okay, again, with this formula here, we're just always assuming whatever we're looking at in terms of particle, that we're moving it from the outside to the inside. Very important concept. So we have to put our temperature in here, and this is converting converting to Kelvin, and so body temperature is 37 degrees, and converting that to Kelvin, so you're going to end up with a body temperature of 310. So that's the put you put down there, it's 310. Okay, and you got your 2 factor there. We've already talked about that, so just plug that in there. And now we have in, and then we have out on the bottom. So in right there, that's going to be 0.05. Out is going to be 5. Run the calculations, and lo and behold, you get 1426 calories per mole. Again, we knew it was going to be negative because we have a nice, lovely concentration gradient out to in. Rounding the value here, so we're really talking about minus 1.4 kilocalories per mole. So for every mole of glucose that diffuses down this concentration gradient into the cell, it's going to be releasing that amount of energy. Now, kind of a side point here, this equation here is in natural log. You can come up with a version using 10 base log as well. You just have to convert between natural log and 10 base log. It's going to involve that number there. This is totally FYI. I'm just letting you know if you want to, you could do that. So again, because the glucose is moving down its concentration gradient, then I knew already I was going to have a negative Gibbs free energy. So this equation here allows me to actually calculate how much energy is being released per mole of glucose. So I think that's pretty straightforward. So now let's make things more interesting. So now what we want to consider is active transport of glucose. And as soon as I say active transport of glucose, I'm talking about putting energy into the system. Because if I'm having to put energy into the system, then that means I'm moving glucose up its concentration gradient. So that's what I kind of want to focus on now. So before I get into that, I'm going to elaborate on kidney, because the example I want to use is from renal physiology. I assume you have a basic idea of how the kidney works. The kidney basically cleans up the blood. Blood goes into the kidney takes, alters the blood, and so that you're excreting or you're making urine. That's all the things you want to get rid of. And basically the kidney kind of filters your blood. So you kind of knew all that already. Well, the functional unit of a kidney is a nephron. And the nephron, a key component of a nephron is going to be a glomerulus, and this is what I have here in the cartoon. A glomerulus is just a very specialized capillary, and so you see that in the cartoon here. And so what you have is you have blood going into this capillary, and it is going through what we call an afferent arteriole. So the blood courses through this capillary, and then the blood leaves the capillary, and it's going to be coming out in what we call the efferent arteriole. So one of the things that's very special about that capillary is a pretty high pressure system. So what you have here then is, because it's a high pressure system, it is literally squeezing out a portion of the plasma, pushing it out of the blood, out of the capillary. And so what I have is this little cup here that is ready to receive the content that's being squeezed out of this capillary, and this is called a Bowman's capsule. And the fluid that is being squeezed out, once it's in Bowman's capsule, also has a very specific name. It is called a filtrate. So the filtrate was plasma, and now it is percolating through the kidney. So as the arrow says here, the filtrate is going to go into a tube, and I'm going to extend this so I can make my point here. So this would be a renal tubule. And because this part of the renal tubule is closest to the glomerulus, we actually call that the proximal tubule. And the term proximal is used as you would use in any other type of description of anatomy. Proximal means closer to a reference point. Distal means farther away. So our reference point here is the glomerulus. So proximal simply means the part of the tube that's closest to the glomerulus. So this is the proximal renal tubule. If there is a proximal tubule, you know there's a distal tubule somewhere, and so the distal tubule is going to be downstream. So I'm going to elaborate on this drawing just a little bit. So I'm going to do here, and I'm going to do here. So I'm going to use this to kind of draw some cells. Okay, there's some cells. So my filtrate, I'm going to go yellow. And so there's the filtrate. It's kind of going through the tubule there. I didn't mean to, the cells are all the way up, okay? So doot. Got that there. So here's the challenge. And that is the filtrate was plasma. And so it has a lot of things in it that were in plasma. And fresh filtrate, recently formed filtrate, has a lot of molecules in there that your body needs. So most of the energy that goes into kidney is the kidney has to remove all the good stuff from the filtrate, put it back into the body, and then what's left is going to be urine. So how does it get it back to the body? Well, let me go ahead and draw this other thing, and that is associated with this tubule are going to be these little blood vessels there. Maybe got a blood vessel here. So the deal is that these cells here are going to be grabbing all the good stuff that you need, okay, taking it from the filtrate, putting it into the cell, and then the stuff that needs to go back to the body will leave the cell, will get into that capillary, and off it goes to be spread to the rest of the body. So that's basically how the kidney works. So let's get specific about glucose. So among all the very valuable molecules that end up in the filtrate is going to be glucose. So I got glucose in there. And typical glucose concentration of plasma is around 5 moles per liter. So I got 5 millimoles per liter. So I got a good chunk of glucose that's in the plasma. Therefore, I've got a pretty good concentration of glucose in the filtrate. I've got to get all that glucose back, because glucose is a precious energy molecule. The last thing I want to do is to be urinating or excreting all those glucoses. My body needs those glucoses back, so it's part of the job of the kidney is to take all that glucose that's in the filtrate and return it to the body. It's going to grab a glucose, put it in the cell, then the glucose is going to diffuse out of the cell. Eventually it will make its way into these little capillaries here, arterioles actually, and they're going to be whisking it away and be spread or taken to the rest of the body. That's basically how it works. Okay, so I'm going to zoom in here to make a larger drawing so I can make my point. So I got 2 big old cells here. And let's just go ahead and say I got my blood vessels associated with it. Got one there. Got one there, and then I got my filtrate, and there's my filtrate there. Okay, so now I've got some glucose in my filtrate here, you see, and then I've got a lot of glucose in the cells here, tons and tons of glucose in the cells. So the object of the game is I've got to move this glucose from the filtrate, get it into the cell, and then once it's in the cell, then it can diffuse out of the cell and make its way into the blood here. So that means I'm going to need a transporter, and that means I need a glucose transporter. So there's my glucose transporter. It's going to grab a glucose, put it in the cell. But you can kind of see the problem here in terms of the energetics, because I got to get rid of all the glucose out of the filtrate. I got to take all that glucose, put it back in the body. Well, if I do that, and I'm just going to go ahead and erase this and then put the yellow back so I can make my point here. There's my yellow. Okay, and maybe I'm down to like my last couple of glucose molecules. I got to get those molecules out of the filtrate. But I have a cell that is loaded with glucose. Do you see the issue here? Now I've got a real steep concentration gradient that I got to fight. So this is going to require energy. So how is that going to work? Well, this is what I want to do now, is to explain a little bit how that works, and that is I have another player involved. And my other player is going to be sodium. Sodium is also in the extracellular fluid. You got loads and loads and loads of sodium in the extracellular fluid. And you'll recall from earlier courses, you have a lot of sodium in the extracellular fluid. You have just a little bit of sodium in the intracellular fluid. So most of your sodium is outside the cell. So if the filtrate is just plasma, and let me go ahead and change this up a little bit here. Okay, we'll just stick with this. Okay, so what we got here is we got sodium, and I got lots and lots and lots of sodium in the filtrate, and I just got maybe a little bit of sodium inside the cell there. So I have a favorable concentration gradient. So what if I were to take this transporter that's designed to transport glucose against this concentration gradient, and I pair it with transporting sodium? So now what I have is a symporter. And you've seen that before. So now the idea is I can take this lovely concentration gradient that I have with sodium, and I can use that, because that's going to be releasing energy, going to be releasing Gibbs free energy, going to be negative. And I can take that energy and take my glucose and push it up its concentration gradient. So the energy that I'm going to need to pull that glucose against its concentration gradient, I'm going to get by the energy released when sodium is going down its concentration gradient. So that's the basic setup. So let's go ahead and hang some numbers on this and see how all this works in terms of the energy involved. Okay, so what's the free energy needed to move the glucose from the filtrate into the proximal tubule? And let's just say, because we're going to need numbers anyway, let's just say that the concentration of the filtrate, the glucose in the filtrate, has dropped to 0.006 millimoles per liter. So that means my glucose here is down to 0.006 millimoles per liter. And so let's just assume that the glucose inside the cell is up to 6 millimoles per liter. So I've got 6 millimoles per liter of glucose in the cell, because as I'm pulling glucose from the filtrate, it's building up in the cell, building up in the cell. So now I got a pretty good concentration of glucose in that cell. So I got 6 in the cell and 0.006 out of the cell as I take my last little bit of glucose molecules and pull them out of the filtrate. Well, that's pretty good concentration gradient. So now the big question is, how much energy am I going to need? How much am I going to put in the system to make that happen. So I'm going to utilize my handy dandy equation here. So I got my 310, got my 2. Again, this is N. So I got natural log here. So N, 6 millimoles per liter. Out, okay, that's going to be my extracellular fluid. My filtrate is going to be 0.006. So when you run the numbers, what you end up with is 42 and change calories per mole. I looked at the system. I knew that the Gibbs free energy had to be positive. So rounding it, basically what I have is 4.3 kilocalories per mole. So again, talking about or reminding you what we talked about in the last lecture, I need more than that. Okay, that's just kind of the break-even point. I need to exceed 4.3 kilocalories per mole if I'm going to use, if I'm going to put in energy in the system to pull that glucose up its concentration gradient. So exactly 4.3 isn't going to do it. I need more than 4.3, but that's kind of my baseline or my reference. So that's kind of cool. But I just got through saying, okay, well, I'm getting my energy from my sodium gradient. Well, then let's check out and see what I'm getting from my sodium. So I do have my sodium glucose transporter, and it's a symporter, as you know. So I need some numbers to calculate the Gibbs free energy with the sodium movement. And so let's just say that the sodium outside of the cell is going to be 140 millimoles per liter. Inside is going to be 10 millimolars per liter. So that's my concentration gradient. So again, what I'm trying to do is I'm trying to move glucose against a pretty steep concentration gradient from here to here, but my sodium concentration gradient is 140 and 10. 140 outside, 10 inside. Again, just draw a cell here, so I have 140 millimolar on the millimolar per liter on the outside and 10 millimoles per liter on the inside. So again, I got a nice little concentration gradient, but that's what that is. So question is, how much energy am I releasing? Well, again, since I'm going downhill, I'm going for high concentration, low concentration, I know my Gibbs free energy is going to be negative. So let's just plug in some numbers. So I have 10 on the inside. I have 140 on the outside. I got 1637 calories per mole. Again, because I'm going down a concentration gradient, I know it's going to be negative. So rounding, I've got basically 1.6 kilocalories per mole energy released when that sodium is going down its concentration gradient. So there's some energy. But there's also a problem. How much energy do I need to move that glucose from the filtrate into the cell? Well, I need to be north of 4278 or 4.3 if I'm rounding. Well, this is only giving me 1.6 calories, 1.6 kilocalories per mole. So that's not enough energy to do the job. But you'll note something else here that's interesting. That is, sodium is a charged particle. It's an ion, charged particle. So when I'm moving sodium, I'm moving charge. So there are electrical forces afoot here. That's what's happening here. So you already know that a typical cell, the inside of the cell is going to be negative relative to outside the cell. And so if I have a positive sodium here and inside the cell is negative, I've got an electrical force that is pulling that sodium in. Now, how negative? Typical is going to be minus 70 millivolts. That's a typical resting membrane potential. So I have another force is help pulling the sodium into the cell. And so if the electrical force is pulling sodium into the cell, there can be you can find out how much energy is being released. Again, I can calculate the Gibbs free energy. But I'm dealing with electrical forces. But luckily, there is a form of the Gibbs free energy where I account for that. And here's the formula here. So what I have here is I have a Z value. The Z is going to be the valence of the molecule, and so it's +1 in this case. I got Faraday's number there, F23062. Do not memorize that number. You know, I'm just, if you need this to work a problem on an exam, I'll give you that number. So you have that. And then I've got to plug in the resting membrane potential. Okay, so here's a tricky part though, and that is I said the resting membrane potential was minus 70 millivolts. This equation up here, I have to convert that millivolts to volts. So I've got to go and put it in the formula as 0.07 volts. So that term there has to be in volts for this equation to work. So I have my numbers. I'm just going to plug it in, and I get 1614 calories per mole. Okay, that's close to what I had with the concentration when I have 1637. But when I round them, they both end up being negative 1.6. That's just kind of accidental. Okay, so what this is telling me is that for every mole of sodium that is going down the electrical gradient here, I'm going to be releasing about 1.6 kilocalories per mole. Again, releasing energy, which is why it's negative. So what I do now is I have a quantity of energy being released because of the concentration gradient, and I also have a quantity of energy being released because I'm drawing a positive charge into negative. All I have to do then is add the two up, and when I add the two up, I get minus 3.2 kilocalories per mole. So that's accounting for both the electrical force and the concentration force. Well, that's kind of cool. So now for every one sodium that is moving into the cell, okay, again, I've got my, where am I right here? So for every one sodium that is being pulled into the cell, that's going to get me 3.2 kilocalories per mole, but I still have a problem. How much do I need to get that glucose? I need north of 4.3, and I'm just sitting here at 3.2 kilocalories. That's still not enough energy. That's a problem. Except, this is a really cool thing, and I'm going to redraw this for you here. Boom, get there. And I've got my filtrate is here. Okay, I've got my little bit of glucose there, tons of glucose here. Okay, I've got my symporter here pulling glucose in, and then I have my sodium part of it. Okay, sodium going down the hill because I got lots of sodium here and just a couple of bit of sodiums in there. Okay, well this system here, again, that's only going to give me minus 3.2 kilocalories. That's how much is going to be released. Not enough. But many of the symporters, the transporters that work in the kidney on this, many of them utilize 2 sodiums for every glucose. So now I can use the energy for 2 sodiums. Well, if 1 sodium gets me minus 3.2 kilocalories per mole, then what do? Multiply by 2, and now what do I get? This symporter here, because it's utilizing 2 sodiums, now my energy yield is 6.4 kilocalories. Again, negative meaning it's being released. Well, 6.4 kilocalories is well beyond the needed 4.3 kilocalories I needed to get that glucose across its against the concentration gradient. So there you have it. The fact that many of my symporters in the kidney are pulling in 2 sodiums for every glucose, now the energetics work. Now I'm yielding more energy pulling those 2 sodiums in, plenty to get that glucose up its concentration gradient. Again, this is a theme that you see in kidney. It does the same thing with amino acids. I got amino acids going into the filtrate. I got to get all those amino acids out, so I have to have a transporter to do that. And the story about amino acids is very similar to the glucose. I actually have symporters that will pull amino acids out of the filtrate, putting them into the cell, and they are paired, again, with sodium. So I'm using that concentration gradient of sodium to help with that. And some of those symporters, again, like this one here, will actually utilize 2 sodium, so it has plenty of energy to pull those last few amino acids from the filtrate into the cell and then on to the rest of the body. You see this theme also in the GI tract, because in the GI tract you got to reabsorb all that sodium. All of that glucose. You got to reabsorb all those amino acids. So you're going to have a similar theme in your GI tract, or a challenge from the energetics is I'm having to pull some of these molecules against a pretty steep concentration gradient, and most of the time it's going to be utilizing the sodium concentration gradient to get the energy to actually accomplish the goal here. So I think this is pretty cool. So you got to account for the concentration gradient of sodium, then you're accounting for the electrical component of the sodium, and then you have to have a symporter that uses 2 sodium. Then that gets you enough energy to do the job, to get that glucose, those last little bits of glucose in the filtrate against its concentration gradient, so you can load that cell up, and then as it loads that cell up, then you're going to have glucose via facilitated transport to move down its concentration gradients and will ultimately end up in the blood, and the blood can take the glucose away to the rest of the body. So pretty clever system we have going on here. But again, it goes to my general point is there's no free lunch. If I am moving something against the concentration gradient, the energetics has to be there. And of course, we see here that it does. So next time, I'm going to do one more example with the Gibbs free energy, and then we'll be done with this section of the course. So I'll see you next time. What I want to do in this section is to go over a concept that you probably first learned in high school. You certainly learned it in freshman biology, and that has to do with where ions are distributed. You know, how much of the ions are inside the cell, how much of the ions are outside of the cell, etc. So I want to focus in on 2 of them, and I want to focus in on sodium and potassium. So you know the vast majority of your sodium is outside the cell. So I got a lot of sodium out here and just a little bit of sodium inside. We talked about that a lot in the last lecture. The other one as I want to talk about, and that is potassium. So potassium, most of my potassium is actually inside cells, and I just got a little bit of potassium on the outside of the cell. So this distribution of potassium and sodium in terms of in the cell versus out of the cell is really important for many, many biological processes. And of course, we saw in the last lecture how important it was to maintain that sodium concentration gradient so the kidney can do its job, so the GI can do its job, etc. So if I have this distribution, the challenge is, how do I keep this distribution? Because you always got leaking and moving and things like that. And again, no surprise to you, we have a sodium-potassium ATPase pump. And we can cartoon it out here. And so we know that this pump here is going to be taking sodium from in the cell and pushing it back outside, and that this pump here is going to be taking potassium that's outside the cell and pushing it back into the cell here. So you know you have that. Also, you're quite aware that this is a 3-to-2 deal. So for every 3 sodiums that are pumped out of the cell, it's pulling in 2 potassiums. It's also the fact that I'm moving charge, so every time this pump spins, I am pushing 3 positives out, pulling only 2 positives in. So every time it spins, I'm netting 1 positive charge being pushed out of the cell, and that actually helps in maintaining, in part at least, my resting membrane potential. And we're going to go ahead and say that the resting membrane potential is minus 70 millivolts. That's going to be our little fiction number here. So what I'm saying is that this sodium-potassium ATPase pump is a contributor to whatever the resting membrane potential is. There are a lot of other things that contribute to it, but the sodium-potassium ATPase pump certainly influences that resting membrane potential. And so we know that the inside of the cell, typical cell, is negative relative to the outside of the cell. So we have all that going on. Well, you can look at this and say, hey, I'm pushing sodium against its concentration gradient. In this case here as well, I'm pushing the sodium, because it's positive, pushing it into a positive environment, so that's even more of a challenge to do that. The potassium, I'm pushing it against this concentration gradient, so I got a lot of potassium on the inside, a little bit on the outside. But it happens to be for potassium, since potassium is positive, I get a little bit of help on that electrical, the potential being negative on the inside. So the electrical force favors potassium coming in, but the concentration force does not. So I got a lot of moving parts here. And so the cool thing is, if I know concentrations of these electrolytes, and if I know the resting membrane potential, I can actually calculate how much energy it's going to take to spin this pump. How much energy is it going to take to push that sodium out and to push that potassium in? Because, looking back up here in the name of the pump that you all know, it is a sodium-potassium ATPase pump. So this is going to be having to need quite a bit of energy to run this thing. Where does that energy come from? It comes from the hydrolysis of ATP. The A's means that this pump here has an enzyme on it that has the ability to peel a phosphate off that ATP. And then I've got ADP, but I'm releasing energy, and hopefully that energy that is being released is going to be enough to supply this sodium-potassium ATPase pump. In fact, it is, which is why we're here. But we want to get a better idea of exactly how much energy am I going to need to put into this system. Well, we can run those calculations. So let's utilize the tools that we have, and let's do that very thing. So we have to make some assumptions. So the intracellular fluid, we're going to say sodium is 15 millimoles per liter, potassium is 140 millimoles per liter. Outside the cell, sodium is 145 millimoles per liter, and potassium is 5 millimoles per liter. And we're going to just assume that the electric potential is minus 70 millivolts inside relative to the outside. So now we want to figure out how much energy is exactly going to take to run this pump. Well, let's utilize our tools. So what we have here is we have our standard equation that we use, and we're just going to plug in. Reminder, in is on top, out is on the bottom. So we plug this in for sodium, and what we get is negative 1.4 kilocalories per mole. And you say, wait a minute, I'm looking up here and I'm trying to push that sodium out, which requires energy. I do the equation and I get a negative, which means it's releasing. So what's that all about? Reminder now, a very important concept with this equation here. Remind you that that's the inversion of it. So what this equation is assuming is that you're going to take sodium and move it in the cell. That's what that equation is going to tell you. And since you have lots of sodium on the outside, a little bit of sodium on the inside, when you run this equation, this is literally telling you if sodium were to go down its concentration gradient out to in, that's the convention, out to in, then it's going to be releasing 1.4 kilocalories per mole. So you got that. Now let's do the same thing for potassium. Plug in the numbers and I get plus 2.1 kilocalories per mole. Well, how come that's plus and that's negative there? Same deal. Again, this equation here is assuming I'm taking a potassium and I want to move it into the cell. Well, if I'm moving potassium in the cell, I'm moving it against a pretty significant concentration gradient. So according to the equation, I'm going to have to put energy into the system, which is why this is positive. Okay? So again, that's an important concept I don't want you to forget. So this equation is to make an assumption that I want to take something out of the cell and put it into the cell. Well, what we're going to find out here that that's not the assumption we're going to hold, but we're just going to flip some signs to make that work out. So here we have the energetics. So we still have not accounted, though, for the electrical force because inside the cell is negative, outside is positive. So we have to run through those calculations. So again, we have our formula here to do that. Run through all that, and we find out that for the sodium, it's going to be a yield of 1.6 kilocalories per mole. Negative, which means I'm releasing energy. Now, why is that not a surprise? Again, because we're just we're just looking at it from the vantage point of the sodium going from out to in. So what's in? It's negative. What's sodium? Positive. Okay, so I got positive going to a negative, release of energy, lo and behold, negative gives free energy, 1.6. Then we do the same thing for potassium. I get negative 1.6 for the same reason. Potassium is positive, going into the negative. Now you'll note that these numbers here are identical. Why are they identical? Because this formula here is only considering charge. This formula here doesn't care whether we're talking potassium or sodium. They're both +1. So you're going to get the same number. So what this is telling me here is that if these two were to move into the cell, this is the amount of energy that I'm going to be releasing. So now this is where the careful thinking has to be. So let's now give an account, being careful with the negatives and the positives. I'm wanting to know total here, what is going to happen when I am moving the sodium out and the potassium in. Okay? So careful on this one. So for the sodium, what I'm going to need here to move it into the cell, okay? So what I'm going to get as far as the concentration is going to be releasing energy, okay? So then I have to consider moving sodium into the cell. I'm going to again be releasing energy in terms of the electrical. So that means that every sodium that goes into the cell, I'm going to be releasing. I got to add this plus this, and I get 3 kilocalories. It's minus because I'm releasing energy, but I'm doing it 3 times. Okay, or I want to calculate the energy for 3 times. So 3 sodiums, hypothetically going into the cell, is going to yield me minus 9 kilocalories per mole. Okay, got to think carefully about this. So what I'm doing is I'm running all the numbers assuming the sodium is going into the cell. So if I move 3 sodiums in the cell, I'm going to have a total release of energy of minus 9 kilocalories. Now let's do the same thing for potassium. So we saw for potassium, how much energy am I going to need moving potassium into the cell? Well, potassium is against its gradient here, so this is going to be positive. Okay, then I add, looky here, because it's positive going into the negative, now I'm releasing energy here, so I add these two up, and so my net energy is plus 0.5 kilocalories. So I'm still needing to put energy to move that potassium in, but I'm getting a little bit of help with the electrical part, but I'm still on the plus side, so I'm still going to need a little bit of energy to move the potassium in. And if I want to move 2 potassiums in, then I just simply multiply that by 2. So that means then I'm going to need 1 kilocalorie per mole to move 2 potassiums in. Okay? So summing all of this up, okay, in terms of the energy involved, I simply take the 9 plus the 1, and that's going to get me 10 kilocalories per mole. So let's go back and make sure we're going to be careful how we're thinking about this. What I'm wanting to do is I am wanting to account for what if I have to push 3 sodiums out. Okay? Well, I know 3 sodiums going in is minus 9 kilocalories. That's how much energy is released. So pushing sodium out, my reference point is going to be 9 kilocalories putting into the system. You see the flip there? This is telling me how much energy is going to be released if 3 sodiums go in, but I want to push 3 sodiums out, so I got to flip that sign to make it 9. Okay? So here, what I'm wanting to do is I am wanting to push potassium into the cell. Well, I don't need to flip the sign there. I'm already there. That's 1 kilocalorie because, again, the equation is assuming I'm pushing potassium in, so I don't need to flip the sign there. So that gives me the 1. And so I simply then add the 9 and the 1, and I get 10 kilocalories per mole, okay, that I'm going to need to move 3 sodiums out and 2 sodiums in. Now, going back into what I said earlier, that's my reference number there. I need more than that if I'm going to drive this pump, okay? So 10 is my base. I need to exceed 10 kilocalories per mole in order to move 3 sodiums out and 2 potassiums in. So what that tells you then is that when I hydrolyze an ATP, 1 ATP molecule, I'm going to need more than 10 kilocalories per mole if that 1 ATP is going to spin that pump 1 time. So there you have it. So that's my minimum energy need. When I hydrolyze an ATP, it's got to be north of 10 kilocalories per mole to run this pump. So hopefully that makes some sense to you. And now we have some real numbers in terms of what happens when we hydrolyze the ATP by complements of the sodium-potassium ATPase pump. And again, given the numbers I have here, I'm going to need more than 10 kilocalories per mole to run that pump. Hopefully you found this helpful. Talk to you next time.